All right. So first order of business is a week from this Friday is exam. I didn't even look. Exam 2, right? We've only done one exam. Okay, so exam 2 is a week from Friday. So that's Friday. This would be the 20. This would be 31st, right? Halloween. And the topics are everything before the start of the second law. So everything we've done so far. Um, and so we're going to do for the next couple days, we're going to do sort of an outline of the topics we've covered so far. We've done that once or twice before already. I'm going to just keep, doing that periodically just to sort of try to put a framework in your head of all the topics, how things fit together, stuff like that. Try to emphasize some of the connections between topics or whatever. And then after the outline, we'll get into the start of the second law of thermodynamics. That's the stuff that won't be on the exam. So this outline is sort of like to help you with this exam. Anybody have any questions about this?
So is this will this change if we get further into second law, or how?
Will what change?
The amount
The topics?
of content on it.
No, this is what the test is on, no matter what we do before then. Yes, every test is cumulative, so you got to go back to the beginning material. I would recommend, as soon as you can, start this process of getting ready for the test. And I would say to do it, just go to problem set 1, problem 1, and say, do I remember how to do this question? And if you do, then you can skip to the next one. If you're hazy on it, then work through it, and I think that's a good way to just really be ready for I think basically any question I'll ask on any exam, you could look through the daily problems and say, okay, that one's that's the same approach as this problem, So there's not going to be anything you haven't seen before, really. It's just a matter of getting it fresh in your head, and being ready for those kind of questions.
Do you suggest doing that before skimming over lecture notes and stuff?
I think skimming lecture notes is helpful. That's what to do to get ready for the quizzes. I'm trying to do these outlines so that, those outlines, I think if you kind of keep that stuff in your head, sort of function the same as looking through the notes. But I think reading through the notes is always helpful. I really think the way I think about it, by the time one of these classes is done, your notes should have fingerprints all over them. They should have notes in this pen, and then the pen you used a week later, 2 weeks later, or whatever. You should be just steadily going over those, trying to get to the point where, where what the topics are. I look back on some of my college classes, a lot of my college classes, and I think there were classes where I did a ton of work, did a ton of problems or whatever. But if someone asked me what this class was about, I would have had trouble answering that question. And that's really what I'm trying to correct with a lot of my approach to things. If your grandfather takes you aside and says, what did you learn in this class? I want you to be get in a comfortable chair, grandfather, because I'm about to lay it on you for 3.5 hours, Yeah.
You want students to have a better understanding rather than just like punching a number in.
Well, yeah, I want you to have a framework in your head of how all the things fit together, what the class was about, why I tried to do this and this. That's my goal, you know. Instead of just like I did problems with my hair on fire until 2 in the morning every night. Like I want you to have a little more structure than that. I mean, partly I think that's the nature of engineering. Like I don't want you to leave these classes uh, having done a ton of math and shown that you're smart or whatever. I want you to leave here with a tool belt full of tools, you know, and like then when a problem comes up, you can say, I have a tool for that, you know, and here's where I got that tool, and here's how it fits in with other tools that might not work as well, you know, for this specific case. So, okay. Um, so here's number 2. We got a turbine. It's at steady state. It says how much power it's developing. Um, it says what the mass flow rate is. It gives you an inlet temperature and speed. And it gives you a exit state. You know, it's a saturated vapor, and it gives you a pressure and a speed. And we want to determine the inlet pressure. Okay, so it's steady state. So I'm going to just jump right to the steady state version of this, of the first law for control volumes. So we have 0 is equal to Q dot for the control volume minus W dot for the control volume plus M dot times the quantity H inlet plus V inlet squared over 2 plus GZ inlet minus M dot times the quantity H exit plus V exit squared over 2 plus GZE. And we have velocities in this thing. So I'm going to leave those velocity terms in. Neglecting potential energy. Yep, it says it explicitly there. So we're going to forget about that. So I'll cancel those. And then we're given the power that's developed. This is a turbine, so it's going to be outputting power. And so this W dot is going to be a positive value of 23 times 10 to the 6 watts. And it doesn't say anything about the heat transfer. But it's, oh, it does. You're right. Thank you. Yep, insulated. So this is 0. And so I can put this in as 0 is equal to negative 23 times 10 to the 6 plus M dot was given 40 times H inlet plus we're given a speed at the inlet. So 35 squared over 2. And then minus 40 times H at the exit plus 120 squared over 2. And we're trying to figure out the inlet pressure. So now let's think about what we know at the 2 states, or at the inlet and the exit. Okay, so at the inlet, it is steam. We have a temperature of 360 degrees Celsius. At the exit, it's a saturated vapor. And we know that the pressure is 0.06 bar. I think in the website, it gives this stuff in kilopascals, not in bar. So this is 1, 2, 3. I think that's 60 kilopascals. 1, 2,
Six.
1, 2. Yes, 6. All right, so we can look some stuff up right away, and that'll. So at the exit, we can go right to the website, and we can punch in that it's a saturated vapor, so that's a quality of 1, and a pressure of 6 kilopascals. This is steam, so we're talking about water. We use international. The pressure is 6 kilopascals, very low pressure. And then the quality is 1. And we have an enthalpy of 2, 5, 6, 7 times 10 to the third. I'm doing everything in SI units so that I can use those velocities. And we get, so 23 times 10 to the 6 is equal to 40 times the quantity HI plus so 35 squared over 2 is 612.5. And then we have minus 40 times the quantity. And I have all these values. So this is 2.574 times 10 to the 6. So 3 times 10 to the 6 is equal to, let me subtract all the other stuff. So we got minus 2,4,500 plus damn it, 40 times 2.5. So plus 1.030 times 10 to the 8 is equal to 40 enthalpy at the inlet. And so I get that specific enthalpy at the inlet is 3.148 times 10 to the 6. This is in SI units. So this is in joules per kilogram. And now I have two properties at the inlet. So 360 degrees Celsius and this thing. It does it in kilojoules, so that's 3,148. And so we get a pressure of 2590 kilopascals. So HI of 3.148 times 10 to the 6. And a temperature of 360 degrees Celsius with the website says, I forgot what it says, 2590 kilopascals. Any questions about that? And that's all for that one. Mm-hmm. Any other homework questions you'd like me to go over? One nice thing in this class is we have a lot of time before the exam. We've already covered all the stuff for the exam, so we have plenty of time to do homework questions and still get through the outline and still get fully ready for this exam. So feel free to bring homework questions over the next few days. Okay, so now I want to go back to the beginning and just sort of go through an outline of what we've covered so far. So this is an outline of topics before the start of the second law of thermodynamics. The second law of thermodynamics gives us a ton of calculation power. This is a really cool one. It's sort of philosophically interesting. We're going to bring up entropy, talk about what that is, kind of intuitively, and then we'll have all this ability to use it in equations too. Okay, so I started out with an introduction. And I started out with pressure. And the main result for pressure was, okay, so I'm going to leave a line blank here. We're going to fill that in a second. But we had this equation that said the pressure at the lower point is equal to the pressure at the higher point, like altitude, height-wise, plus rho g h. Okay, so that's a really important equation for us. It doesn't apply all the time, though. what are the conditions under which this equation applies? What? Uh, so that is, I think, moving in the right direction. There are two conditions. Its steady state isn't quite what it is, because really we're talking about a single instant. Steady state applies to processes. But I think you're thinking about the right thing. Anybody else? So
Same material.
it it does have to be the same material. That is not one of the ones that I was going to say.
Is that it needs to be continuous
Yes, so the first one is it has to be continuous
and then have rest?
and at rest. Yep.
I had to cheat for that and go back.
Yeah. Okay, so I mean, in this class, we see a million cases where these things don't apply, where this equation doesn't apply. For example, we do calculations where you have a pressure inside like some kind of vessel that's higher than outside the vessel, and we calculate forces on the walls. The only reason that's possible is because that fluid is not continuous. You have the vessel separating the air on the outside from the air on the inside. And then also at rest, remember with all this stuff with control volumes, we have a continuous fluid that's going through, say, a turbine or a nozzle or whatever. And you have, so even if the height of this fluid isn't changing, you'll have, like in this last example we just did, we have a really high pressure at the exit, a really low pressure at the inlet. That's a continuous fluid with no change in height. The reason the pressure is changing is because that fluid is not at rest. Okay. So always with these equations, like using these equations is about remembering alongside the equation what are the conditions where it applies. The Pythagorean theorem doesn't work very well if you try to apply it to a cylindrical solid. You know what I mean? It's all about like applying it in the right conditions. And then we use this equation in two ways. The first one was barometers. And anyone remember what you use a barometer for? There are two ways that we talked about to calculate pressures. The second one is going to be a manometer. So which one do we use for which thing? Barometers are for measuring atmospheric pressure. Think like barometric pressure. And then the second one is manometers. And those are used to measure the pressure in an enclosed fluid. And then the second part of the introduction was calculating the work of expansion. And this has continued to be a really important thing in every problem. Even when it doesn't come up, it's always should be in your head that this is something that you can use if you're given information that helps. And the work of expansion says W is equal to the integral from volume 1 to volume 2 So that's from the volume at state 1 to the volume at state 2 of P dV. Remember, this is important because we most often talk about volume in terms of a specific volume. But remember that this is the extensive volume that you need here. And in order to compute this integral, you need either pressure as a function of volume, or if you're lucky, constant pressure. What's the most common case that we've dealt with where you can express pressure as a function of volume for computing this integral? Just trying to jog your memories on this stuff. So as you go through these outlines, like go through it studying or whatever, I think this is kind of the way you should think about it. Like just ask yourself questions. Do I remember this? Do I remember where we talked about it? What kind of questions does it come up? Yep.
I forgot what it's called,
Yeah.
but it's the PV to the power of
Yeah.
A equals B.
Yeah, exactly. So it's the polytropic processes is the name. And we've even done some problems where there's a relationship between pressure and volume that's a different form. We did one where it was linear in one of the daily problems. But the most common case is where you have something that's like pressure times volume to some exponent is equal to a constant. And whenever you have that, you should think like, okay, it's very likely that I'm going to calculate the work of expansion here. And then after this introduction part, we talked about the first law of thermodynamics for closed systems. So the closed system is as opposed to control volumes. This is where you're tracking a single amount of material as it goes through time, as things happen to it over the process. And so the first way we dealt with this was that the change in energy is equal to Q minus W. And you always have to remember that Q is energy added to the system by heat. And you always have to remember that W what is going on here? W is energy removed from the system by work. And also remember that this delta E is made up of kinetic energy plus potential energy plus internal energy. And of these, this is the one that's most often important to us. There were some simplifications that you could look for in using this form of the equation. So first of all, if it says steady state, then the change in energy is equal to 0. There's also one that we haven't talked about too much yet, but it's going to come up a lot in the next section, and that is anytime you hear something described as a cycle, okay? A cycle is not the same thing as steady state, but it does say that at instant 1, at the start of the cycle, all properties are the same as at the end of the cycle. And so that, with this equation, means the same thing as steady state. Okay, so steady state means that the whole way through the properties don't change. A cycle means the properties can change, but when you finish a cycle, you're back where you started. Then we talked about the differential form of the first law. And this one says dE dt is equal to Q dot minus W dot. The first thing I want to bring up about the differential form is what are the indicators that you would want to use the differential form? So the first subtopic here, indicators to use the differential form. You know, when would you use it as opposed to that standard form? Well, the first thing is if it's giving you energy values in terms of watts. Okay, watts are joules per second. So if it's using units of watts, that's joules per second. And that suggests that those things are, that it's giving you energy transfer values on a per time basis. And so that's going to fit naturally into that form. Second is if it's giving a time dependence for the energy transfer variables. So for example, if it says work is being done at a rate of 7t, where t is in seconds, that's a time dependence on that energy transfer equation, and that likely means that you're going to have to use that differential form. And then the third one is anytime that you're using any of the heat transfer equations, you most likely are going to have to use the differential form. Almost certainly you're going to have to. Because remember, those heat transfer equations are always given as like Q dot is equal to something, you know. So, anyways, if you remember those three things, that can, and you know, then you can often just use those as a really effective way um, to not waste your time trying to fit stuff into the standard form of the first law and to jump right to the differential form. Um, Second, the simplifications that come up for the differential form of the first law. There's really only one that comes up regularly, and that's steady state. And that means that dE dt is equal to 0. I mentioned the cycle thing before, as so if you're using the standard form of the first law, you can think of steady state and cycle as meaning the same thing. But if you see something referred to as a cycle, it doesn't mean that dE dt is equal to 0. So this is really the only one for the differential form. And then third, we talked about the heat transfer equations. Um, and when you use these, remember that you cannot trust the signs that come out of the heat transfer equations in applying them to the first law. So you can't trust the signs from the heat transfer equations when using the first law. So basically, you'll from the heat transfer equations, you'll just get absolute values, and then you have to think, is energy going into my system or leaving my system due to this heat transfer? And it's easy to tell because heat transfer always just happens from a higher temperature to a lower temperature. Um, so of these, the first one is conduction. And the conduction equation says Q dot is equal to negative kappa times A times dt dx. The first thing to do is ignore that negative. That's always given as part of the equation, but remember these signs don't really mean anything to us. Kappa is the coefficient of thermal conduction. You'll get that, be given that for a specific material. A is the area perpendicular to the energy flow. So, for example, if you're talking about conduction through a window pane, this is the area of the window, you know. So, like if we're talking about heat transfer through one of those windows there, the area we'd be talking about would be, say, what do you think that is? 2.5 meters high by 1.5 meters wide. That's the area A. And then remember that uh, dT we're always going to be talking about linear temperature change with respect to um, distance. So you can always just think of this as the change in temperature divided by the total distance. The next one is radiation. Um, and there are two forms that we talked about. The first one is Q dot sub E, so this is heat emitted from a body, is equal to the emissivity times the Stefan-Boltzmann constant times the surface area of the material times the temperature to the fourth. This equation is general, but it's not very useful for the first law. Anyone remember why this form isn't useful for use with the first law?
Something about the material color.
So the thing here is that what we need is net heat transfer, okay, in order to use the first law. And this doesn't tell us anything about heat that's being absorbed by the material. This only tells us about heat that's being emitted from the material. So it's only like half the information we need. You know what I mean? So there is a form of this that applies in certain cases that we can use, and that is that the net heat emitted is equal to the emissivity times the Stefan-Boltzmann constant times the surface area times the quantity temperature of the body to the fourth minus the temperature of the surroundings to the fourth. I'm going to put a box around this one because really for the kind of analysis we do, this is the only one that's useful. This only holds for a smaller body surrounded by a larger body. So that's a pretty specific application. But if you have that condition, you can use this with the first law. Okay? Yeah.
Professor, what? So the first one is emissivity, the like E.
Yeah.
What is the?
That is a constant. It's 5.67 times 10 to the minus 8, I think, in SI units. It's called the Stefan-Boltzmann constant. And let me just finish this section real quick. So the last one is convection. And that one says that the rate of heat emitted is equal to H times A times the temperature of the body minus the temperature of the fluid. And this one is not like the radiation equation is a law of physics. This isn't really a law of physics. It's kind of a curve fit thing. That H has to be determined experimentally for your specific application. So for a specific application. Okay, and that's it for today. And then I'll continue next time with material property relationships.